So this is a situation, I have some kind of handle that I'm turning, and we're trying to calculate for this bar what's going on. This one is acting more like a beam, which you're not worrying about yet. We're worrying about torsion. Which piece is in torsion? It's this vertical member right here. We don't know what the load is. We're trying to design something, we're trying to design the maximum load for this vertical member. And what we know, we can measure that the diameter of that would be 0.015 meters. Because of the material, we can get a certain shear strength, which is in terms of tau allow. I put 120 times 10 to the 6 pascals. They write that, sometimes that's written megapascals. I always like to write everything in terms of meters, pascals, and then I just convert the units over. That way I don't have any messy units going on. Units catch your errors. That's one thing I like to stress. Okay, they also have another constraint. We have our angle of twist. Our phi allow is 5 degrees. So in other words, this handle, we can't twist past 5 degrees. Another thing we'd look about whatever material that is, we have the shear modulus is 80 gigapascals, or 10 to the 9th pascals. So one thing that helps me is I'm going to try to draw it in terms that we know. We don't like, when we're doing torsion, usually we're used to having a horizontal member. I'm going to draw it as if it was a horizontal member. Okay, and I'm going to represent this torsion. So first of all, this member is this member here on its side. This support is down here, and this torque is on the end. Now I'm looking at this torque. It's according to my right hand rule, as I'm closing my hand, that's the direction P is pulling, and so it's down into, the arrow would be down into this column here. And on our picture, I could write a double arrow. Okay, a couple other things I forgot to write on here is that this total distance across is 0.3 meters. And this is 0.5 meters tall. And on this picture, that would be 0.5 meters long. This torque on this side, this is an applied torque on the end, and it's equal to the load times the distance. Now I could look at it as, if I look at just one side, half that distance is 0.15 meters times P, and then I multiply that times 2 because I have 2 of them. Or I can look at it just from one end and say it's 0.3 meters times P. It's going to give you the same answer either way. So whatever makes most sense to you, do that. So my torque, 0.3 meters times P. Notice that I keep my units in as I go. And P right now, I'm going to keep unitless, just so that my answer presents me with the units. You'll see what I mean when I get to the end. Alright. So first thing I think of, I look at both of these two allows. Those are two different constraints that I'm given. This one would be given by the material, and this one would be given by the design, say the contractor or designer of this project gave me a slip of paper that says I can't go beyond that. Those are two things, two rules I have to follow. So I have to be within both of those bounds, which means I can't go above either of those limits. So I need the one that is most constrictive, so I don't go past either of them. Now I can compare my shear stress and my phi as is, but that would be pretty difficult. I would have to go through the problem for each of those constraints and then compare my final answers. However, there's an easier way. I can go through my problem once if I just deal with the problem now. The easiest way to do that is to convert one of these into the form of the other. or I take my phi allow and see what would that be in tau allow. So, just going to separate my givens from my solution. Okay, so if I have phi, I know that my phi equals gamma L divided by R, and G equals tau over gamma. If I solve this for gamma, tau over G, now I can sub 2 into 1. See how I took those basic formulas and I created a formula that gives me what I want. Alright, so I'll probably want to take my phi allow and convert that into shear stress, allowable shear stress. So I'm going to want to solve this for tau. Okay, now I can just plug in my phi allow, my allowable angle of twist, and I will get how much shear stress that would exert. Now this is in degrees. There's no degree units in my tau, so now I have to convert the degrees into radians. My G was given. Radius, I have my diameter, so I just divide my diameter times 2, or divide it by 2. Alright, and this looks like an L on the bottom, and that was our length from our picture, 0.5 meters. If I plug that into my calculator, I will get my tau allow according to my phi allow is 104.7 times 10 to the 6 pascals. Now let me write my other tau allow right next to there, just so that we can compare. So these are my two constraints, and I can't pass either of them. So if I were to start at 0 shear stress and slowly increase, I would break this one first. That's the one that I need to worry about. I'm going to do the rest of my calculations using this, and I don't have to worry about this anymore. Because as long as I'm within these bounds, I'm okay. I don't even have to worry about that one. And another way of saying that is that our allowable angle of twist governs the situation. Alright, so now I can continue. So our whole objective, going back to the beginning, our situation, we were trying to find our allowable load, our force, our P. We're trying to solve for P. And now we know what our constraints are, what we need to focus on. So we have a formula over here with P. Let's start with that. P times 0.3 meters equals torque. And in my mind, I'm thinking, okay, I know torque and my shear stress are related. And so I need to find a way to put this equation inside of that equation, which doesn't end up being too hard. So notice we have shear stress equals our torque times our radius over our polar moment of inertia. This is just like we've done in the past, except our torque has a variable in it, our unknown P, but we know everything else. So we have 104.7 times 10 to the 6 pascals equals P times 0.3 meters times our radius 0.0075 meters. I just divided the diameter by 2 in my head. I know, impressive, right? I could divide by 2. Polar moment of inertia. Again, we have our equation that we memorized. Our diameter 0.015 meters to the 4th. And look, we only have P left. Maybe I should have, in retrospect, maybe I should have rewritten this equation like this. And I would have saved myself a step. So I was solving for P. I just need to multiply or divide this over, so I isolate P. And I'm just going to plug it into my calculator. Okay, good thing I did this beforehand. And I get 231 newtons. Alright, I can still do a little unit check here. If this is newtons, if I plug this in, I should get pascals. So even if you mess up a little bit like I did, you could still check your units and find a possible mistake. So if I plug in newtons here, this is newton times meter, and I'm dividing by meters to the 4th. So that means that this is meters squared over meter to the 4th. It is newtons over meters squared, which is the definition of a pascal, which means my units are good. And we are done with that problem.